While it is important for rockets to have good engines, engines are useless if a rocket cannot be controlled. In an atmosphere, rockets need much more powerful steering methods because of the air. When a rocket tries to turn in the atmosphere, the air that was pushed around it by its nose cone will push it back into its original orientation. The rocket must overcome this external force in order to actually turn. In the atmosphere, rockets will also act as pendulums. The engines at the rear are heavy, just like the weight at the bottom of a pendulum. Gravity will try to pull the rocket into a position that is perpendicular to the surface of the planet because of the engines. This makes it tremendously difficult to control rockets while in an atmosphere. To overcome this problem, more powerful control mechanisms are used. One of those methods is fins. Fins work by separating the air into two parts. They then make one of those parts of air move faster, so it has lower pressure. Then the higher pressure air will try to move towards the low pressure, but it can't, and instead it just hits the wall of the fin and moves the rocket. Fins usually control air pressure by using flaps. Moving a flap over to one side of the fin will make the air on that side of the fin have to travel a longer distance in the same amount of time, so the air moves faster. Fins usually work in tandem with the fins that are across from them. This is because if a fin worked alone, it would induce a force that did not go through the center of mass and would therefore introduce a spin, which is called a roll, in addition to the attendant effect. In addition to the term roll, scientists use pitch and yaw to describe the movement of rockets. A roll is when the rocket spins on an axis without changing the position of the cockpit, merely rotating it. Pitches and yaws are when the rocket tilts in a direction. When using fins, pitch and yaw are controlled by using opposite fins that will move the flaps in the same direction. Rolls are introduced by opposite flaps moving in opposite directions. Rolls work because one side of the rocket is trying to move one way and the other side of the rocket is trying to move the other way, so it spins. Rolling is a very important maneuver because almost every rocket performs a maneuver called roll to align with its azimuth. An azimuth is the inclination degree of the orbit that the rocket is trying to achieve. By rolling to align with its azimuth, a rocket has the ability to perform their tilts using only pitch or yaw, not both at the same time. This makes it so that the rocket can have a smaller flight computer and can therefore have less mass. Fins have been used on many famous rockets, including the Saturn V. Despite their high control, fins get worse the higher up you go, and will eventually stop working entirely. Another atmospheric control method is something called either engine gimbal or thrust vectoring. That is simply when you push your engine on a joint of some kind so that you can tilt it slightly and push your rocket in a different direction. The terms engine and thrust refer to the fact that you're moving the engine and the thrust stream to control it. The term vector means the direction of a force, so it represents how you move your thrust, while a gimbal is a kind of joint that you can put your engine on. On a rocket, at least one engine is required to control pitch and yaw, while a second engine is required for roll control. This is again because you need to push a rocket in two opposite directions at the same time in order to control roll. The flaw with engine gimbling is that your engine will have to be on in order to use it. Outside the atmosphere, more precise control methods can be utilized. One of those is RCS thrusters. RCS stands for Reaction Control System, and RCS thrusters are little engines on the side of craft that can be fired in order to control pitch, yaw, and roll. The problem with RCS thrusters is that you can't just use any old engine as an RCS thruster. You need to use engines that can turn it on and off very quickly. And they also have to be small enough to fit several of them on the sides of spacecraft. Traditional pumped engines require too much time to get the pumps going, but you could use a pressure-fed engine as an RCS thruster. The problem with that is that RCS thrusters are generally fired rapidly with little time between each burst. To solve this problem, people needed to use hypergolic propellants in the engines. That way a spark is not even needed. That comes with a problem too. Hypergolic fuels are toxic, so much effort is going to be put into loading them, and if there are humans on the spacecraft, then extra protection for the humans would be required. Instead, you could use a single propellant or monopropellant thruster. One kind of monopropellant engine is a cold gas thruster. In a cold gas thruster, a single pressurized gas is held in the fuel tank. When a valve is opened, the gas will leave the tank. This creates an engine that can be turned on and off very quickly, is non-toxic, and is relatively cheap, but is also not very efficient. Another kind of monopropellant engine is a decay-based engine. In that kind of engine, a fuel is run over a catalyst that causes it to decay and expand. This kind of engine has fast shut-off times because all you need to do is open a valve to turn it on or off. It also has higher efficiency than a cold gas thruster, but the most common fuel is hydrazine. Hydrazine is toxic, carcinogenic, corrosive, hypergolic, and must be kept heated. This makes it very hard to deal with. Ground crews that deal with hydrogen have to wear full-body hazmat suits with a self-contained oxygen supply. The price of those materials can bring the cost of launching a rocket up by hundreds of thousands of dollars. Because of this, people have been developing safer alternatives, but those have not been adequately tested yet. For long-duration missions, RCS thrusters are not the best because you will eventually run out of propellant. To solve this, mechanical attitude control systems have been developed. One of those is a reaction wheel. Reaction wheels are metal wheels that are attached to a motor and surrounded by lubricant and ball bearings. When the motor is activated, the wheel spins, and a force that is equal and opposite to the rotation of the wheel will be applied to the craft. This causes the craft to spin. In order to maintain control along all three axes, 3 reaction wheels are required, one for pitch, one for yaw, and one for roll. But reaction wheels will break if the force of friction ever exceeds the force exerted by the motors, so most craft have 1 or 2 spares. You could also use a control moment gyroscope to control the movement of your craft. In a control moment gyroscope, a constantly spinning wheel is rotated on a gimbal. This produces a force that is perpendicular to the spinning wheel. In the default position, the perpendicular force from all the wheels cancel each other out. When the wheels are turned, then the forces become unbalanced, and the spacecraft turns. Both of those methods experience a problem known as saturation. Saturation occurs because when the wheels stop spinning or are returned to their default position, the craft starts spinning in the opposite direction. Think of it like when you try to stop a wheel that is spinning quickly, you start being pulled along with it. This makes so that the wheels have to constantly maintain speed in order to keep the spacecraft straight. But the spacecraft is constantly being acted upon by external forces, so the wheels must constantly apply more force. Eventually, the wheel will not be able to spin any faster. In order to stop this, a spacecraft will slow its wheels down while being kept in the correct orientation using RCS thrusters. Another control method uses electromagnets. When the electromagnets are turned on, the spacecraft will point either north or south. This works well, but it eats up a lot of electricity, and it gets worse the farther away you get from Earth's electromagnetic field.